Good morning, dear participants. Welcome to the fourth day of session, and we are very fortunate to have a professor from IIT Kanpur, Dr. Shalabh sir, who is a professor from Department of Mathematics and Statistics. And let me introduce sir. Sir has done postdoc from University at Germany in 2007, and also from Pittsburgh, USA in 2002, and PhD from University of Lucknow in 1996, and masters in from University of Lucknow 92, and same undergraduate from University of Lucknow in 1990. So her specialization is statistics and economics, and the research interests include linear regression models, econometric modeling, measurement error models, missing data models, panel data models, restricted regression, spatial models, and forecasting techniques and sampling theory. And sir has a wide publications, and sir has written many good books, and I love this statistical analysis of designed experiments, and that's motivated me for inviting sir to this STTP program. And I'm very happy that sir has accepted this request, and we are very fortunate to have sir in to deliver his lecture here. And sir has won many awards and recognitions from in national and international level, and he has more than 25 years of experience in different universities, institutions in India and as well as in abroad, and has published more than 100 research papers in national and international journals, and has authored 4 international level books, and more than 5.4 million copies of the books have been downloaded, and has worked in applied statistics and involved in different projects for the government of India, and has received fellowship and awards of national and international recognitions and remarkable achievements. And sir is well known for his courses, which is already available online in both MOOCs and Swayam NPTEL. You can go through, and it has participations are more than 15,000 students as of date. And I am very thankful, sir, for accepting the request. And it's my pleasure that you are giving this lecture on regression theory, modeling, as well as applications, sir. So I request participants to make full utilization of sir, and try to interact with sir, and try to get as much as possible with this lecture. Thank you, sir. Thank you for accepting this request. And I have made you co-host, sir. Now you can share your screen.
Okay, thank you very much, Harun. It is my pleasure also to give a lecture in this session where I can believe that many say intelligent and learned participants are there. And as a teacher, you always feel happy if your participants, if your students are good, who are. I always say in my class that for me means if my student move one step towards me, I will try to move 2 steps before them. But if they try to move in the 1 step backward, possibly I will move 4 steps backward, because your students are your motivation who forces you to learn. The fact is this: as a student, we never learn the subject, but we learn the subject only after becoming the student, when you have the responsibility of your students. So I'm also great. So I'm actually always grateful to my students who have made me learn many things. Otherwise, no human being wants to work. That is how the God has created. So anyway, so just to give you here a background that, well, I'm going to talk very simple, very elementary, very basic. And one thing I must accept that in the next 3-4 hours, I cannot make you expert in the area of regression analysis, but surely I can give you sufficient background, and possibly you will know that where you can use these tools. It is something like at your home, whenever we have headache, we try to take a Disprin. Whenever we have fever, we try to take a crocin. We don't understand what are the ingredients of those medicines. But at least we know that, okay, if I have headache, then I have to take this medicine. And if I have this thing, then I have to take this medicine. Once I know, then whenever I am in trouble, that is the human tendency, that whenever the problem comes over us, then we try to understand all the facts and figures of that problem. So that is my approach also. I will try to give you here sufficient background. And yeah, I'm keeping in mind that my audience is from engineering background. They are not from a statistics background. They are going to be user, but they are not the blind user. They are means educated users. So once they want to use anything, first of all, they should know what is this tool which can be used at any in any problem. And after that, once they are trying to use, definitely they are going to use the software. So because yeah, manually now nobody computes all the things. So whatever is the outcome of a software, that they must understand, because getting an outcome from the software, that is not difficult. Either you have to click or you have to write just a one line command, and then you will get everything. And then whenever you are trying to use any software, different softwares have different commands. So it is practically impossible to list all the commands to get the regression model from say different software. But anyway, I will try to show you that how the outcome of a software look like. And all the software's outcome will have some adjustment, that some term is on the left hand side or in the top or in the bottom, but the contents are going to be more or less the same. So my objective is very simple, that given a software outcome, because I believe that once you know how to fit the model or how to get the model, you can very easily learn how to input that data. And because the different softwares also have different ways to enter the data. Once you enter the data, after that you get the software, and then you try to get the outcome. So getting an outcome is something like, if you have seen that there is a some this uh, some person who looks into your horoscope, and then horoscope has a structure like this one, where something is written like Chandra, Mangal, Brihaspati, etc., etc. And then the Pandit tells you based on that combination, okay, your Chandra is here, your Mangal is here, your Brihaspati is here, so you are going to get a promotion or not. So that is the same thing in the software outcome also. The outcome will remain the same, but if you try to show the same horoscope to different Pandits, they will try to tell different outcome. Well, I don't believe on these things, so I don't try to interact with them, but means I have seen. By this example, you should not understand that I am a fan of those things. Well, but I have seen common people, and yeah, as a statistician, I have to work with common people only, so I have to think like them. So this software outcome is also like that. That you should know that how different values are coming together. You cannot say that only one value is going to be there. So, for example, if you say based on just the value of R square, if I say you are trying to say that model is good or bad, that may not really be the correct thing. And if you try to think from the point of view of a medical doctor, if a person goes to the doctor with some ailment, the doctor always tries to ask many things: blood pressure, blood sugar, height, age, weight. And then when the doctor looks at all the parameters simultaneously, only then the doctor is able to get the means correct outcome, correct diagnosis. So that is the same thing with the outcome of a regression analysis. That unless and until you understand the interpretation of each of the value, it is very difficult to take the final conclusion, because you are not interested in what is happening in this part, this part, this part, or this part, but you are always interested in the totality. Means at the end of the day, you ask the doctor, tell me whatsoever be the problem in my body, whether this medicine is going to work or not. So that is my approach in this lecture also. I will not be going into much details of the mathematical proofs, but surely you have to believe that whatever I'm going to tell you, they are based on some strong statistical theory, strong mathematical proof, and so there is a validity. So I'm going to give you here only those results which have been established in the literature. There is no controversy. Right, because this, if you try to see this regression analysis itself, an area of research where people are trying to discuss and trying to develop. And honestly speaking, everything is not also developed. It is just like in the medicine, you have not, as a human being, we have not developed all the medicines for everything. Similar is the case of statistics also. that as soon as you are trying to handle a complicated problem, the complexities increase, and then you have to choose a suitable model. But surely in this 4-hour lecture, I'm going to deal with the basic standard model. And after that, depending on the needs, whether this violation is not acceptable or something like whatever are the experimental conditions, you have to choose the suitable model and you have to make suitable modifications, number one. Number two, that's my experience and that is my suggestion to you all, that don't expect that when you get the data from the experiment in the first shot, you can get the outcome. That can be done only with the God. We are only the human being. And yes, the reason why I accepted Arun's request, because we at IIT Kanpur, we have here a department of mechanical engineering, and that was the first department where I interacted with some of my colleagues here. And for the first time in my life, I saw that if I want to use the regression analysis, then it is also working. It is giving me some results which are really true, which mechanical engineering feels that, well, these are the correct values. And this happened in the way that one day my colleague just brought me some data. And as usual, everybody expects that a statistician know everything, and he or she has a direct connection with the God. So I will take the data, I will go to my office, I will ask the God, now you tell me what to do. God will let me know that these are the values of the parameter, and I will come out of the room and I will tell you. Right. So this cannot happen. So, well, he's my good friend also. So I just blasted at him. I said, well, what is this nonsense? Means you have conducted something in the wrong way and you want him to put here the right analysis. But then he's my friend, so I cannot ignore him. I said, you forget about it. You give me some time, and now you try to conduct the same experiment in the way I'm telling you. I will give you the outcome. And then, yeah, he just associated one of his PhD student who were working on that problem with me, and we reconducted the entire experiment. And when we conducted the entire experiment, then I just conducted the experiment according to the needs of the regression analysis. And yeah, when he brought me the problem, then I was convinced that, okay, in case if I try to use here the regression analysis in this particular way, then possibly I will get the outcome of the, or outcome as the answer of the question which my colleague is asking. Because that is very important as a statistician to understand what really you want. Means you want something and then I am trying to give a reply of something else, then the things are not being done. And then we conducted the experiment, and while keeping choosing the values inside the experiment, I kept the basic assumptions of the regression modeling that we learned in the theory, that I have to choose this value and I have to conduct this experiment in such a way such that the basic assumption for the applicability of the linear regression model, they are satisfied. And believe me, that was the first experience of my life about 15 years back. Then for the first time, I could understand myself that at least, yes, the statistics work in real life. Statistics is working truly on the data. But the only thing is this, if the right tool is exercised in the right direction, and you have to choose what tool you want to use, whether you want to use regression analysis and factorial experiment, fractional replication, partial confounding or not, etc., etc., then only you will get the right answer. It is something like this. If a person has some body ailments, there are many options to get the blood test, urine test, X-ray, MRI, ECG. But the doctor has to tell the right test for the right disease, and then only the diagnosis is going to be the correct, and then the treatment is going to be could be correct. If somebody has fractured the bone, and if the doctor says, okay, you get your blood test, possibly that's not going to work. So that is the same objective when you are trying to learn this statistics as a mechanical engineering. I'm not expecting, or might not be expecting that you should know all the mathematical details or the theories behind this subject, but at least you must know that what are the conditions where you can apply this tool. Because yeah, means everything cannot be applied at in all the situations. You have to understand that where they are going to be used, and based on that, you have to first check that when you are trying to use the tool, then whether the basic assumptions are getting satisfied or not. The fact is this, my experience is that nobody is really bothered in taking of those basic assumptions. And in real life, I can share an experience with you where I can explain you that how important is this to have the satisfied that way, that the basic assumptions should be satisfied. My mom had got the fever, and it was and she was having some fever, and we thought that it is possibly viral fever, and she went to the doctor, and doctor diagnosed that she is going to have to typhoid. So then we said, okay. Then I got confused that how it is possible that typhoid is there, means there are no symptoms. So then we went to another doctor. And the typhoid test was saying yes, this is correct, that the person has got a typhoid. And the doctor said, well, the test is correct, and the doubt of the doctor is also correct, that given the symptom, there is a possibility that she can have the typhoid. But the basic condition in the test of typhoid is that in case if the person is continuing for the fever for at least 5 days, only after that, if it is conducted, then it will give the true result that the person has really a typhoid. But this test was conducted only after 3 days. So, well, the test is telling something, but that is not dependable. So when it comes to my own health, my own family, I am bothered about assumptions. And then I simply criticize the doctor that, okay, this test is going to be valid only when it is conducted after the 5 days of body temperature, continuous body temperature. But the doctor got it tested only after 3 days. So that's the real example of violation of the basic assumption of a test. So regression analysis is just like a test. So now I will request you, I will try to give you here, or I will try my best efforts to give you here a basic assumptions. Once you have these basic assumptions, I know that whenever you want to use it, you can go to the software, but before that, surely you will try to consult a book or something where you can see that the tool which you are using here is satisfying all the basic assumptions. And we have here all the tests by which you can actually get a fair idea whether the tests, whether those assumptions are getting satisfied or not. But surely one thing you have to understand, this regression analysis is a 1 semester course at my place. And yeah, I'm going to give you here in 4 hours. So I will try my best to comprehend it. But I hope you will excuse me if I am unable to give you all the things what you expected. Just before talking to Dr. Arun, that many of you are possibly interested in using the regression equation in different algorithms, right? And this model is going to act as an input for those algorithm. So I assure you that unless and until I bring you to the stage where you can get a model, I will not leave today. Right. So getting half an hour earlier or half an hour later, it will not make much difference. But if you don't understand, possibly it will make a difference for me. So I will now share my slides, possibly. Let me try to figure out. Yeah. Can you now see my slides or not?
Yes, sir.
Okay, so I will just begin. Yes, and if any the problem. You just stop me at any time. It will not create any problem for me, because sometimes we say in the talk, no, you are allowed to ask only at the end. It is not like that, right? And I'm sure that even if you stop me 100 times, my concentration will not be broken. That much I know. Right. Okay. So now, in case if you try to have a look at this screen, you can see here, this is only an outcome of our software that is from the R software. That's a free software. And here I have conducted a regression analysis. And when people get this type of screenshot printed on their research paper, they become very happy. But the main thing here is this: they have to, means my objective is that, well, you are getting here a multiple linear regression model, but it is very important for you to understand what is happening where. Right. So now we are beginning with this screenshot where you cannot understand anything possibly. Now I will try to start my lecture, and at the end, my last slide is going to be the same, where you are going to tell me what is the thing which you have not understood. Right. So let me now begin my lecture here. So you see, we are going to consider here a modeling technique. So this modeling technique means there are two types of modeling techniques, which are linear models and non-linear models, right? And then, yeah, in practice, if you try to see, there are many situations where a non-linear regression model or a non-linear model might be more suitable. But let me accept the fact that handling the non-linear model from the statistical point of view is not an easy job. So many times what we try to see, that we try to look into the data structure, and we try to partition the nonlinear models into different segments so that they can be converted into linear models. And then we try to fit the data for those typical linear models in those sections. And then we try to combine them together. So ultimately it comes to that: if we can understand how to fit a linear model and how to get the outcome from there, after that, that will be helpful for you to understand the complicated models. So now I'm just going to take here a very simple example. Well, means I didn't, means I knew that most of the participants are going to be from the mechanical engineering, but I thought that, okay, I don't know about all of them. So I just took a very simple example. Actually, this example was created just to make you understand. And that's an example where we all, either as a faculty or as a student, we have gone through with these things. So, we are always interested in the marks in the examination. So we know that the marks of the student depend on several factors, like a number of hours, say, in a week of what the student studies, number of assignment is submitted every week or every month, number of hours of play, and so on. So all these factors that we know, they are uh, going to affect the marks in the examination. Right. So, and suppose we are interested in finding out the relationship between the marks of the student and these variables like hours per week, and number of assignments submitted, number of hours of play, etc. And actually, you can just convert these variables to your engineering. My problem is this: I don't know anything in engineering. Right. My only qualification is my friends are from engineering background. Right. So you can just translate all these things. Marks of the students they are the outcome of your some experiment, which is going to depend on a couple of factors, which can be translated in terms of a number of hours of per week of study, number of assignment, number of hours of play, etc. So this is how you have to example. So if you see here, I have taken here 20 observations. Right. So it is as simple as that. I have first selected 20 students, and I have selected their marks, what they have obtained in the examination. That is indicated by here Y. And then number of hours per week of study, that is X1, number of assignments submitted per month, that is X2, number of hours of play per week, which is X3 here. And so now we want like to find out the relationship between Y and jointly with X1, X2, X3. Right. Now, who can ask that why I have taken here 20 students? The simple reason is because I don't have a space in my slide for accommodating more than 20 students, and 20 students I can type so that you can see them clearly. Means if I type 100 numbers, possibly you cannot see them. Right. So now my thing is this: we know that there is going to be a functional relationship between the marks of students and with respect to these variables. So I can express that relationship here. You can see here it is given here. Y is the function of x1, x2, x3. Now my question here is this: I want to know the form of this f. That is unknown to us. That is known only to the God. Right. So, and this form of this f can be linear as well as non-linear. And we say that this relationship is known to us only when this form f is known to us. That is the same thing what we have studied in the class 9th or class 10, y is a function of x and so on. Right. So whenever we are trying to conduct an experiment, we have got here two types of variable. One are the input variables and the other are the output variables. So input variable, they are also called as independent variables. Output variables are called as dependent variable. For example, I know the experiment in which I was working, my colleague was trying to set different this current, voltage, etc. And then the outcome was some material that was drilled from some metal, right? So in that case, the current, voltage, etc., they were my input variable, and the amount of material which is being carved out from that drilling, that was the dependent variable. And we wanted to know the relationship that if somebody wants to carve out, say, this 2 grams of material, then what should be the current, what should be the voltage? Or if I put some current and some voltage, how much is the material that is carved out? And that was based on some laser, some rays, etc. So the objective here is that we simply want to determine the relationship between the dependent and independent variables and in the best possible way. And that is going to be a model, right? So model is simply a mathematical relationship between input and output variables, which is trying to describe the experiment or the phenomena or the relationship between the input and output variables in the best possible way. Right. So now if I ask you here, what is the model, right? So if you try to see why you are talking only of the mathematical model, we always say, okay, I want to be just like my father. And there is always a code of conduct between the teacher-student relationship. That is also a model. Sometimes you say that, okay, I want to be a teacher like that teacher in my life. So what we want to say, that whatever are the features which are contained in that process, I want to follow those things. For example, whenever I see the advertisement for Fair and Lovely, I always try to put the Fair and Lovely so that I can also become fair as well as lovely, just like the hero. Right. So that is the sort of relationship. So I believe that if I try to give the input variable as the fair and lovely cream, possibly my outcome will be like as a hero. Right. Whether this happens or not, that's a different thing. But anyway, that is the sort of model. So similar is the mathematical model also. And one thing you have to keep in mind that whenever we are talking of statistics, the statistician has no right to change or alter the process. Right. The example which I took, in which I control the experiment of my friend, there I simply collected the input and output values. I had not changed anything in the machine or in the process. And the biggest challenge is that we have to work only on the basis of a small sample, but you want the outcome which is valid for the entire population. Right, and the sample is expected to have all the features of the population. Right, so these are the role under which we are trying to work here. Now, if I ask you a very simple question, that you are trying to work with the process as an experiment. So if I give you here two options, that the process generates the data or the data generates the process. The truth is this, that the process is generating the data. Data is not generating the process. Right. So what is really happening? So if you try to see into the blue figure, blue boxes, we have here a process which is trying to generate the data, and there is some mathematical relationship between the process and the data, or some the relationship can be expressed in a mathematical way. Now, what is really happening? That we don't know this mathematical relationship. The process is also complicated. We cannot see inside the machine that how different components are working. But what we can see here, we have only some data on input and output variable. So now what we try to do here means, if you try to see what are you trying to do in your experiment, you are trying to conduct the experiment. You are trying to get the data, and then you want to find out the mathematical relationship of that process, that how the input and output variables are going to behave. So don't you think that you are going in the reverse direction? You just accepted that a process is generating the data, but now you are trying to use the data to know the process. So that is the objective in the case of regression analysis. So the literal meaning of regression, that is the dictionary meaning, if you try to see, that is means to move in the backward direction. So move in the backward direction, we are trying to observe the data, and then we are trying to move in the backward direction to find out the mathematical relationship. And that is why this is called as regression analysis, right? So now, so we are going to consider here only the linear models. So in the linear models, you are going to have different types of components here. So we are going to have some outcome that is going to be indicated by some random variable, and this outcome we are denoting as y. Right. Usually we have the mathematical function y equal to fx, where y is the dependent variable which is dependent on x. So that is the same formulation we are trying to take here. And then we believe that the outcome is dependent on say couple of independent variables, and suppose they are dependent on k variables. So we simply write in mathematics y is equal to f of x. So I am writing here the input variable here as say x1, x2, xk. Right. Now we are trying to assume some relationship between this y and x. So you know that when you are trying to write down the equation of a line, y is equal to mx plus c. So you are trying to write down the equation between y and x, but that is going to be determined by the values of c and m. So m and c are the parameters of that line. So those parameters I'm trying to indicate here by say beta 1, beta 2, beta k. Well, you don't get scared with this the Greek symbol, because that is only a myth that the Greek symbols are difficult to interpret, and we believe in the statistic that as soon as we give the Greek symbols, people get scared. But the rule is very simple. We try to denote the variables on which we can collect the data by this English alphabets, Latin letter like as A, B, C, D. And the parameters of the model, they are going to be indicated by the Greek letters. So we are trying to write down here this model here as a y is equal to function of x1, x2, xk, and the parameters beta 1, beta 2, beta k. Yes, right. Those parameters can be different in numbers, but it depends on the setup. Right, but at least we are legally assuming that every variable can be characterized by one parameter. Right. So, and plus I'm writing here some term here you can see epsilon. So what is this epsilon? I will try to explain you that that epsilon is the random error component. Right. Random error component means, for example, if you If I ask you a very simple question, what is the room temperature in the room where you are sitting? Means you will say it is, say for example, if you ask me in my room, this is in the Kanpur, it is the winter time. So in the night, the temperature may go up to 7, 8, but during the day, it's about, say this 22, 23, or say to 20, 21, 22, 23. But if you ask me within this room where I am sitting, what is the temperature of the room? I will say simply, okay, 21 degrees. But is it really 21 degrees? The temperature close to my this laptop, which is bubbling the heat, the temperature is going to be more, and the temperature in other corner of the room is going to be less. So if you try to see, there is no play. There are means the temperature is not the 21 degrees in the entire room, but there are some smaller variation, and we just cannot control them. Similarly, when you are trying to use some current or voltage in a real life in any experiment, there is always some fluctuation. So you believe that you have put the indicator of your machine for say 5 milliampere and voltage as some value. But do you think that exactly the same value is being continuously supplied to your experiment for say 20 hours? There can be small variation, but those variations are really beyond our control. We cannot control them. So we try to put all those things, all those observations which we cannot control, which we cannot observe in the sort of basket, which is called as random errors, and that is going to indicate the indicated by this epsilon. So you can see whatever you cannot measure, whatever are the things which you cannot quantify, they are going to be in the basket of epsilon. But this doesn't mean that that those things which you can do, and if you are not doing it, they can also be put into the epsilon. That is the same story that your student comes to you and the student has got less marks, and you ask that, and he says no, that is random. But once you ask him that, okay, how many hours you have studied, and he says that okay, he has not studied at all, then would you try to contribute the variation in his marks due to random error because or because of a known factor? That is because of the known factor. So in that case, this epsilon will also contain some information which they could have been known to you. So it will not give us a good result. That is my very simple interpretation. We have some mathematical aspect also, right? So epsilon is indicating that the relationship between y and with this independent variable is not really going to be 100% exact. There will be some variation. Now, means this in case if the variation is less, possibly it's not a big deal. But if the variation is high, then this is a point of concern. And definitely, when we try to take this epsilon to be zero, that means there is no randomness in the model. Then the model is going to be called as mathematical model. In fact, that is the basic difference between the mathematical and a statistical model. That the statistical model always takes care of the randomness in the data, whereas in the case of mathematical model, there is no randomness and the model is completely exact. Now, this is the choice. Means I'm not trying to um, say appreciate or criticize any model, but this is the basic difference, and that you must know, because many times we are trying to use the mathematical model also and uh, in our analysis. So the term here model is broadly used to represent any phenomena in a mathematical framework, right? So this is how you have to understand. Now there is a big deal, big question that many times people try to think that that in case if they try to plot a data and then if there is a linear trend, that means the model is linear. Then no, that is not actually true. Uh, According to the definition of the linear model, a model is termed as linear if it is linear in the parameters, not in the variable. For example, if you try to plot the data on say the relationship like y equal to say 4x squared, that is like a parabola. So if you try to plot it, the scatter diagram will be something like this, some non-linear, but that belongs to the family of linear model. Yeah, I'm sure that this is going to be a surprise for you. What you are saying that by looking at the scatter diagram that you try to plot the data between x and y, you can know that whether the relationship is linear or not. That is correct. Right, because this is the relationship which is theoretical. But definitely when you are trying to do it in practice, you have only the set of data, and based on that, you have to take all the observations from there. Right. So what you are doing that when we try to plot the data, if the relationship looks to be is looking like a linear one, definitely there is a linear model. But in case if the relationship is non-linear, you have to just analyze that whether a linear model can be fitted or not in that case also. That is what I wanted to tell you. Right, and remember that the linearity or the non-linearity of the model is not described by the linearity or non-linearity of the independent or the explanatory variables in the model. Yes, input variable, independent variable, explanatory variables, they are the different names, right? So that is what you have to be watchful. So whenever we are trying to think about the model, there can be linear model, there can be non-linear model. And when we are trying to find out the model on the basis of given set of data, when we are trying to handle the linear model, then we have a linear regression model. When we are trying to consider the non-linear model, then we have here the non-linear regression models. And in linear regression model, it is linear in parameters and linearity in the terms of variables. That is not a necessary condition. Whereas in the case of non-linear regression model, it is non-linear in parameters and linear in say variable that is not necessity. Right. So as I told you that what is the meaning of this regression? Regress means to move in the backward direction. So what are we going to do? We are simply going to use the data to get the statistical relationship between the input and output variables. Right. So now we try to consider this example and we try to model it. So we are simply trying to take the same example and we try to find out the relationship between y and x1, x2, x3, which are going to indicate the number of hours of study, number of assignments, and number of hours of play. So we can assume here, you can see in the last line, I have written here a linear relationship, y equal to x1 beta 1 plus x2 beta 2 plus x3 beta 3 plus epsilon. So this is your actually a sort of here model, which is trying to describe the relationship between y with respect to x1, x2, x3. And now it is associated with the parameters beta 1, beta 2, beta 3. So this model is going to be known only if beta 1, beta 2, beta 3 are known to us. Just like in the equation y equal to mx plus c. Unless and until m and c are known to us, we don't know anything about that line. But once this value of m and c are known to us, for example, y equal to 2x plus 3, we know what is the slope, what is the intercept, where the line is going, etc., etc. Right. So now if you try to see how the experiment will look like. So if there is a, suppose I take here the 4 students and 4 students are, they have studied, say, on, and we try to collect the data on x1, x2, x3. For example, if you try to see here student number 1, that student number 1 has got here 180 marks. And the student has studied for 34 hours in a week, and the student has submitted 3 assignments, and the student has played 15 hours in a week. Similarly, the student 2 has got 116 marks, and the student has studied for 12 hours in the week, submitted 1 assignment, and played 30 hours, and so on. So we try to collect the data on the experiment. So now we have only these values. Now you can see what's really happening. We have only these numerical values, and on these, and on the basis of this of these values, this data set, we want to know the value of beta 1, beta 2, beta 3, and other parameters of the model. Right. So if you come to know, then you say that we have got the model. So now, in order to find out the relationship, what are we going to do? We are going to observe this data and we are moving in the backward direction. Right, and we try to determine the parameters of the model. So in this sense, such an approach is called as regression analysis. Right, the theory, fundamentals of the linear models lay the foundation for developing the tools for regression analysis. Because you see, means if you try to look into the books, you will sometimes find a book on linear model, sometimes a book on linear estimation, sometimes the book on regression analysis. So linear models, we have a sort of a mathematical setup which is trying to give us the foundations for the development of tools in the regression analysis. Right. So, okay. So how are you going to conduct this regression analysis? The first step is that you have to state the problem that you want to solve. The fact is this: people simply try to collect the data and they don't know why they are trying to collect the data. Then you have to make the dependent variable. That what are the variables which are going to affect the outcome, and means each of the step what I have stated here, that is going to have its own consequences. If you try to make too many variables or too less variable, they are going to have different types of outcomes. Then after that, you have to collect the data on the important variable. Then you have to assume a structure for the model, whether it is linear or say non-linear. And then you have to see that how are you going to fit the model. That means how are you going to find out the parameters of the model? Because in statistics, we have got different statistical ways. Possibly you might have learned or heard the name of maximum likelihood estimation, principle of least square, or even now this computational based techniques are also there. So based on that, if we try to hit a model, hitting a model means we are trying to obtain the model. And once we have obtained the model, then we try to see whether it is really reflecting the truth or not, whether it is close to the data what we have obtained or not. And then we try to validate the model, we try to criticize it, we want to appreciate it. And then finally, means after a couple of iteration, actually, this model becomes the final and that is ready for the use. The model which we had obtained with my colleague in the mechanical engineering, that took almost 6 months, and then we have to say try about 25 to 30 formulations. And every time we check that which of the model is giving us the data which is very close to the data which was being obtained from the experiment, right? So now, in order to understand this philosophy, in this lecture, that is the first lecture, we are just going to consider one independent variable. Because in the case of one independent variable, possibly I can give you the basic fundamentals. How are you going to work? And once you know that how you have to work with one variable, then extending it to the multiple case is not difficult at all. So that I will be trying to do in the next lecture. So when we have only one independent variable, then the linear regression model, this is usually called as simple linear regression model. And when we have more than one, then this is called as multiple linear regression model. So you will see that most of the books in regression analysis, they begin with the simple linear regression model, and after that they try to develop the multiple linear regression model. So, and you can expect that as we are trying to move from simple to multiple regression model, the complexities will increase. For example, if you have only one friend, you are always happy. But the problem comes only when you have more than one friend, then their interaction starts, their relationship complication starts, and so on. Right. So now, so in order to explain you, I will take the same example which I just explained you, but now we are going to consider here that the marks of the student depend only on say one variable. For example, the number of hours of study in a week. And suppose we want to find out the relationship between the two. So I just try to collect here the data of the two columns here on y and x, and where we have collected the 20 observation on the marks as y, and say number of hours of studies say here x, right? So now you can see here when you are talking of a linear model, you can simply assume a model like y is equal to mx plus c, that is going to describe a linear equation. So the same thing now I try to translate in the language of statistics, that in statistics, we always try to represent the parameters in the Greek letters. So we try to indicate them by beta 0, beta 1. So beta 1 is the parameter which is associated with the independent variable x, and beta 0 is the intercept term. So as you know that when you are trying to write down the equation y equal to mx plus c, so what is here c? When if you try to take the value of x to be 0, then the value of the y is actually c, right? And so exactly on the same lines you have to think. And if I ask you there, what is their m? M is the slope of the line. Slope of the line, if you try to see from the mathematical point of view, you also express as dy by dx. That is the derivative of y with respect to x. So from that point of view, we try to call this y as dependent variable, x as independent variable, the parameters beta 0 and beta 1, they are the parameters of the model. And in the context of regression analysis, they are called as regression coefficients. And in particular, the beta 0 is the intercept term, and beta 1 is the slope parameter, and epsilon is the random error component, which is unobservable. All right. So, and if you try to understand this epsilon, I will try to show you graphically also, but it is, so you are assuming it that now here you can see here that you are assuming that the relationship between x and y is completely linear. So what do you expect? That all your data will be lying on this line. Now, definitely in practice, the data is not exactly going to lie exactly on the same line. There will be some variations and the data will be close to the line. So this epsilon is trying to account for the failure of the data to lie on the straight line. And it represents the difference between the true and observed values of y. And this is sometimes called as disturbance term, sometimes this is called as random error or error term, and so on. And there can be several reasons for this difference, that there is a difference between the value of y that you observe in real life and that you obtain from the model, right? And that can be due to actually a couple of factors. For example, sometimes the variable become too much, then you try to delete some variables. For example, if you say, if you have 20 variables, and then suppose you have to invert a matrix of order 20 by 20 or say 100 by 100, well, conceptually you can do it, but when you come to the computational part, it becomes very difficult. So we try to choose the important variables. So, and sometimes even if I know the variable is important, but then we have to remove it because we feel that the contribution of the variable is quite low. It is not zero, right? So this epsilon is just like here you basket in which whatever you cannot measure, you just try to put it inside the basket. Now our objective is now very simple. Up to now we have introduced here only two parameters, beta 0 and beta 1. So now our simple objective is that we want to know the value of this beta 0 and beta 1. Now the question is how to know. Now you can see the complexities or the constraint in which as a statistician we have to work. We have only the data on say xi and yi, and this data is also collected by us by conducting the experiment or by observing it in the real field. And we have to know each and everything on the basis of this data set only. For example, you can see here nowadays people are worried about the COVID vaccines. So they are not sure about the COVID trials and etc. etc. But if you try to see if they want to know whether the COVID vaccine is effective or not, what options do they have? They will simply try to give the vaccine and then simply try to see the outcome, whether the person has developed any symptom or the person is safe or something like this. And based on that data, now they have to forecast what is really happening inside the body of the human being. So you can now imagine how complicated is the life of a statistician. That data is the same. Data is it's simply deaf and dumb. Data is not raising the hand like this and telling us that, okay, this COVID vaccine is effective or not in this case or that case. But whatever is the numerical value, that has to be read, and based on that analysis only, we have to take a final outcome whether the vaccine is effective or not. So that is the same thing also, that you are trying to conduct different types of experiments. And just by looking at the data on the input and output variables, you have to know whether the relationship is really what you are obtaining is really matching or not, is it good or bad. So now, the success of the modeling depends upon how well you can know the values of the parameter on the basis of given sample of data. And for that, various statistical methods can be used now. For example, this principle of least square approach, maximum likelihood. Now, based on the computation, we have also restricted regression. Many things are there, right? So among them, at this level, when we are trying to begin the principle of least square and maximum likelihood, they are the good approaches. So I will try to actually, in your case, both are going to give you the same outcome in most of the cases. That is why I have taken this. Right, finding out the value of the parameter is something like, if I know that the value of the say this beta 0 is 2 and beta 1 is 3, then my model will become here y is equal to 2 plus 3x. And if the beta 0 comes out to be 5, and if the beta 1 comes out to be 7, then my model will become 5 plus 7x. So you can see that estimating the value of the parameter or knowing the value of the parameters on the basis of given sample of data is equivalent to finding out the model. Whenever we say we want to find out a model, if you ask me, I will simply say we simply want to estimate the parameters. Now the question is that under that given setup, how successfully you can estimate the unknown parameter. So now we are going to have only say small n sets of paired observations on say xi, yi, that you try to give the input variable, try to observe the output, then you change the value of input, and then again try to obtain the output, and then you try to repeat this experiment say small number of times. And we assume here that the model which we are going to fit, it is like y equal to beta 0 plus beta 1 x plus epsilon. So now means every pair of observation that you are obtaining, you have to assume that they are also following this simple linear regression model. So this model is going to be satisfied by here all pairs of observation. So I can write down here as a yi is equal to beta 0 plus beta 1 xi plus epsilon I. Right, now if you try to see, this is what is really going to happen. This dots here, these dots are going to indicate the real observation that you are trying to obtain in the experiment. And if you just remove this line, this blue line, and then if you try to look at only at these points, you can see that the points are indicating that there is a sort of increasing trend. So what you try to see here, if you try to join all the points, then there is going to be a complicated structure, but you are not interested in that thing, right? For example, if you go to the doctor and doctor says, and if you ask the doctor that, okay, how many medicines I have to take? For example, if you go to a homeopathic doctor, which are giving usually very small pills, and they will say, okay, if your age is, in case if your age is just 3 years, then you try to take care. Uh, Say here 5 pills. If your age is say this 4 years, then you try to pay 3.5 pills. And if you try to, and if your age is say 7 years, then you try to take 6 pills and so on. You will get badly confused, but you will try to say, okay, just if I make a statement like, okay, in case if your age is say up to 5 years or 6 years, so you can take 6 pills at a time. Right, so you can see here that there is going to be a smaller variation when you try to see the exact age and the amount of medicine, but that will make the life difficult. So that is the same thing what is happening here, that we expect that that one should have a simple model which is easy to interpret. If I try to give you such a complicated model, the life will become difficult. So what we try to find out here, that if you try to observe only on the point, because for a while you remove this line in the thought process, then you can see here there are only points which are indicating that the process is following a sort of linear trend. So we can assume that if the trend is linear, possibly I can fit here a line, which I am giving here as a blue line. But definitely there cannot be a single line which is passing through with all the points. Right. So one option is this. I would try to draw here a line which is passing through with the maximum number of points, in which this distance from this point to the line, for example, you can see here I am denoting distance which is on the lower side of the line, and here the distance is on the upper side of the line. These distances are as small as possible, and these distances are going to indicate the value of random errors. Right. So now we would like to find out a line which is passing through with the maximum number of points, and in which this random error is as minimum as possible. Right. So you can see here in this case, we have considered the vertical difference between those points and the line. Right. But surely I would like to tell you that why only vertical? You can also consider the horizontal, you can also consider the orthogonal, and there are some other techniques also. But the fact is this: when we try to develop the other tools in the regression analysis, then in the case of this one, when we are trying to minimize the vertical difference, all the tools are well established, and in other cases it is difficult to find out those things. So that is why this method is called as direct regression, and this is more popular than any other regression method. We call it as a inverse regression, orthogonal regression, and so on. So now, when we are trying to use the direct regression method, so in this approach, we are simply going to minimize this distance. So you can see here, you have here a couple of points, and every point has a distance either below the line and above the line. So if you try to take a plus and minus sign by denoting that all the distances which are below the line has to be with the minus sign, and to all the points which are above the lines as a plus sign. And if you try to combine all the random errors, so some random errors are going to be positive, some are going to be negative. So if you try to add them together, they may be close to zero. So that will indicate as if there are no random errors, or the random errors are very small. So what we try to do here, that we have here two options: either we try to consider the absolute value of this random errors, or we can square them. So both the approaches are possible, but we consider here the sum of squares, that you try to take the random error, just square them, and then sum all the squares of a random error. So that way we are trying to say that this is the quantity which is indicating the total amount of random errors in the data, and then we try to minimize that random error. Means in statistics, we always want to have an outcome in which the randomness is as minimum as possible. So we try to write down this function, and we try to minimize it with respect to this beta 0 and beta 1. That way we would like to know the values of the parameters such that the randomness in my data is as minimum as possible. Wait, I think there is wait, I think something is happening. Why it is not coming here?
So the slides are
No, I can see on my slides, but somehow it is these symbols are not coming either in this sharing mode. Means I can see on my computer screen, but when it is getting shared, it is not coming. Okay.
Yes, sir. Even in the preview mode, it's seen something, but
Right.
here it
But
is.
but on my laptop, it is visible on the left hand side. Wait, I will just restart this MS. Right.
Okay.
I think this. I don't know why this happens. So now it means so we simply try to find out the value of the parameters such that this random error is as minimum as possible. So now when you are trying to say that you want to minimize the random errors, now statistics and share. And you simply have to just see that what are the different optimization methods by which you can minimize the quantity. So now I will just use here a very simple thing that, for example, we have used the principle of maxima and minima. Wait, let me. X, Y, there are some functions of only X and Y. So X and Y are known to us. So you can compute these two functions, Sxx and Sxy. Right. And this B1 is the value of beta 1. And B0 is the value of beta 0. So now if you try to see what is the difference between the two, beta 0 and beta 1, they are the values in the entire population which are unknown to us. But now you have estimated their values on the basis of given set of data. So you are saying to you are simply trying to say on the basis of the data on say X and Y, you can find out their arithmetic mean as say X bar, Y bar, and you can compute, you can see this SXY and SXX. These are simply the functions of X and Y. And now you can see what you have obtained. You are simply trying to say on the basis of given sample of data, the value of beta 1 can be obtained by this SXY upon SXX, and the value of beta 0 can be obtained as Y bar minus B1 X bar. So now you see this beta 0 and beta 1, they are going to be some population value that are unknown to us. They are only with the God. But now you have estimated them on the basis of the observed values as B0 and B1. So these B0 and B1, they are going to be some here numerical values, right? So now you have done it. And if you try to see the interpretation of this B0 and B1, that is also the same as the interpretation of beta 0 and beta 1. If you try to see beta 1 is simply, okay, I'm sure that, I don't know whether you know this operator or not. Here I'm writing here EY. EY means simply the expectation of Y. That is the, simply you can assume this is the mean of Y. So I'm trying to write down here mean of Y is equal to beta 0 is a constant, so beta 1 is a constant, X is a constant, and then it will be mean of epsilon. So we assume that mean of epsilon, that is the mean of random errors, is 0 in the population. Well, that you can assume that if you have the big population, some values of random error are going to be in the positive direction, and sometimes they are going to be in the negative direction. So in case if you try to take the arithmetic mean of those values, that is going to be pretty close to 0. So under that condition, this EY, that is the average value of Y. And average value of Y, if you try to see, we are always interested in the average value of Y. When you say that the cruising can control the body temperature, say up to 6 hours, that means that is the average value. You are trying to conduct the experiment over a number of people. You are trying to observe their time, and then you are trying to report the average value. So this beta 1 is simply going to indicate the rate of change in the average value of Y when there is a unit change in the value of X. So you can say here, for example, if your X is the number of hours of study, then you can say that, okay, if a student studies 1 hour more, then how much change is going to be there in his marks. And beta 0 is the interceptum, that is a value of means average value of Y when X is equal to 0. Right, and if you try to understand, I can give you a very simple example. Whenever we are trying to conduct an agricultural experiment, we say that when we try to increase the quantity of fertilizer, then the yield is going to increase. So that means you always say that, or you want to know that if I increase 1 kg of fertilizer, then how much the yield is going to be changed. So that is going to be indicated by the beta 1. But suppose if you don't give any fertilizer in the field, do you think that there will be no crop? There is going to be some crop. So that is indicated by the term beta 0, the interceptor. That even if you don't give any input value, some average value of y will be reported. Now, once you have obtained the numerical values of beta 0 and beta 1, we can substitute them in the model, and the model which you wanted to know based on the regression analysis is obtained as y is equal to b0 plus b1x. This b0 and b1, they are going to be some here numerical values. And there is another definition here, fitted values. Now you see what are these fitted values. Suppose you have conducted the experiment with certain value of x, and you observe the value of y. And now you have obtained the data, and you have obtained this model y equal to beta, this b0 plus b1x. So there is going to be some difference between the value which you are observing in the experiment and the value of the y which you are going to obtain from the model. Simply try to give the same input value to the model, and then try to observe the value of y, that is outcome. And obviously, if your model is giving you the same value which your experiment is giving, the model is 100% accurate. And if there is some variation, that means there is some random error between the values which you are observing in practice and the values which you are obtaining from the model. So obviously, if this difference is smaller, your fitted model is better. So right, so this is what I have shown you in the picture also, that these are the points. This is the same picture, but now it has a different interpretation. This is the point which you are observing here, say xi, yi. Now you have obtained this line, this blue line, which is like here y equal to beta 0 plus beta 1x. Now, but now this is the sample equation, like as y equal to b0 plus b1x. Based on that, you are trying to find out the value on this line, and then you are trying to find out this difference between the value of y which is obtained from the model and in the real experiment. Right, and this is called as residual. So you can see here, this is the same thing which you had observed as a random error, but now you are defining it as a residual. So residuals are the values which are based on the basis of given set of data. So obviously, if these residuals are very close to zero, that means you can assume that your model is good. So this residual is defined as the difference between the observed values and the fitted value. Fitted value means I try to put here a hat. So hat means you are trying to give the value of the input variable, and then you are trying to compute the output variable. Right, so now we try to do this analysis and try to obtain this model for the same set of data where we have considering only the one variable. So now this is here the same data, and you see now I try to plot it. You can see here, this is here on say an axis here is x and another here is y. Right, you can see here this trend is almost the linear trend. Well, there is some variation, but that variation is going to be there because because you are working in a real life where the behavior is going to have some random values. So this is going to indicate us, yes, linear model possibly can be fitted. Now, if you try to see, if I try to give you here 4 options on the same picture, what do you see? And then I try to create here 4 models which are indicated by this different lines in the 4 figures. Which of them do you think that is going to be a good model? You can see here, if you are going for this one, you can see that it is quite different from this data. And if you come to this thing, this is also not so well fitted because your line is going like this. You just try to observe my cursor, and your fitted line here is like this. Right, between this line and this line on the diagonal pictures, you can be a little bit confused whether this is a better fit or this is a better fit. So that is why you can draw here an approximate line, but which one is the best fitted, that you cannot say by looking into the picture. For that you need here some analysis. So now you see here, I have just used here the software R, in which there is a command here lm to fit the linear model, and I have to write down here lm y tilde x, and this will give me here this outcome. Well, I'm not interested in giving you the R software command how to find out this model, but I am more interested in the outcome. You see, this outcome will look like this. Now, this is your horoscope. It is giving, now it is very important for you to understand how to interpret it. So you can see here, this is writing here intercept term. Intercept term means it is the value of B0. And here it is writing here X, and then below here is the value 3.407. So this is the value of here B1, right? So based on that, now you can see here, means just to make you confident that I have really done this analysis. So I am just giving you here the screenshot also. So this is just for the information. And now your job here is to understand how this value 75.779 and 3.407 have been obtained. So now you see this is 75.7779. This is the value of B0, which was obtained here from y bar minus B1 x bar, where B1 was given by Sxy upon Sxx. And if you try to substitute all the values, you will obtain here this value 3.407. And here and if you try to substitute it here in the B1, you will get here 75.779. So the software outcome will look like only like this, but you should know how you have obtained these values. And now looking at this outcome, I can write down my model as y is equal to this intercept term, that is the value of beta 0 as B0, 75.779 plus beta 1x, which is the value of, now we are using the estimated value B1, which is 3.407. So now my model becomes a y equal to 75.7 plus 3.4x. And the meaning of this model is marks is equal to 75.779 plus 3.407 into number of hours per week of study. So now you have here a model. That now if somebody asks you that, okay, if I try to study 4 hours in a week, what are the marks that I'm going to get? Now you can give this answer. Right. So this is now you have obtained the model. And this is called here as a fitted model. Actually, the model that you obtain, the statistical name or the official name is the fitted model or the fitted linear regression model. So now means if you try to say here this number of hours per week equal to here 1. So that means you can obtain that how many marks the student is going to get, 75.779 plus 3.407. Now, what is the interpretation of this value? The interpretation of 3.407 is that if the student studies for 1 hour more, then the marks are going to be increased by 3.4. And this sign here, plus sign, that is indicating that the marks are going to increase. If this sign is negative, that means the marks are going to decrease. And then if you try to look at this 75.779, so if you try to put here number of hours per week of to be 0, that means the student is not studying at all. Even then the marks are coming out to be 75.779. Well, that is possible. You are simply trying to take here only one variable into account, as the number of hours per week of study. Right, but you are not asking whether the student has studied or read any book in the library or on the internet or something like this. So possibly even if your variable takes value, the student will get on an average 75.78 marks. Right, possibly he is studying in the class itself and the student is so intelligent that once the teacher is teaching, he is or she is able to grasp everything, and then they are appearing in the exam. So this is how you have to interpret the values. And now if you try to see, if you try to take this data and if you try to plot this line here, this marks equal to 75.779.3.407x, this will look like here this. Right, and now if you try to come to here, this picture, you can see here, this is the picture which is coming over here. Right, so this is the model which is the well-fitted model. Right, so you can see here, this is here the screen shot of the same thing which I have used here. So you can see here this is now will look like. You will see the screen like this one on your software, and out of that it will have actually many things. If you simply want to have here the coefficients, you can use here the special command. But anyway, I am going to talk about more in the next lecture when we have more things, right? So this is how you can obtain the model. Similarly, if you try to see, if you want to find out the fitted model, so how the fitted model is going to obtain, you have here the model. If you try to see here, y is equal to 75.7 plus 3.4x. Now what you try to do here, that you try to take this data, and now you have here the values of x's. You try to give these values of x's to y and try to compute the y as 77 point this something plus 3.4x, and then try to obtain the difference between the two. So that will indicate the residuals and the values which you are trying to obtain on the basis of given set of data. They are your here fitted values. So if you want to obtain the fitted values, you can get here an outcome like this one, which I have copied here. So you can see here the fitted values here are something like 191, 116. So if you try to compare it, it will come to your data that your model is saying that the student will get 119 marks, but the student is getting here 150 marks. Now your observed data is saying that the student number 2 has got 116 marks. And if you try to see in your this model, it is saying that the student has got 116.65 marks. So you can see that, okay, at some point the model is going to work very well. At some point the model may not be that good, but it all depends that how suitably you are or how correctly you are going to take the data and how well you are trying to fit the model. But anyway, these fitted values will give you the values of the outcome variable when the input variables are given according to your experiment, but the outcome is measured from the model. Right, okay. So, and then similarly, if you try to take the difference between the two, this is called as residuals. And you can see here in all the softwares, whenever you are trying to get the outcome, they will always give you the values of the residuals also as a part of the outcome. And if you try to look at the values of this residuals, you can judge whether your model is good or bad. Although we are going to talk about the R square also in the next lecture. But now if you try to see here that the random error component in the first observation here is minus 11. In the second observation, it is close to minus 0.65 only. So you can see here at some point of time, at some places, these values are small, these values are big. So this is going to indicate the fact which you had taken here, that if this distance is more, these residuals are high, and if this distance is less, then those values of residuals, they are less, right? So once you have estimated the values of your here beta 0 and beta 1 by using this expression, you can see here that they are data dependent. Means as the sample values are changing on x and y, the values of b0 and b1, they will also be changing. So they will also have some standard errors, right? So the question is that how are you going to compute the standard errors, and how are you going to compute here the here this here variance here, right? So now what will happen here, that we are going to obtain here the standard errors of these estimators. So we can find out here the standard error for the beta 0 hat, beta 1 hat, as well as their interaction, that is the covariance between the two. Right, and then the variance can be estimated by this quantity here, SS rest divided by n minus 2, where SS rest, you can see here, this is simply the sum of the squares of the residual terms. Well, anyway, I'm just trying to give you here the expression. You don't have to compute this yourself, but then means you have to simply just find it from the software, but the more important part is you have to understand what this software is going to is going to inform you. So we have here one more command here, summary command, which is will give you this type of outcome. So you can see here I am writing here the standard error part, and this is square. So this is the value of standard error of the intercept term B0 12.78, and this is the standard error of, say here, this B1, which is 0.43, and this here the block in the say here point number 1. This is the value of sigma square hat. Sigma square is the variance of the random error. So now you have a fair idea by looking at this software that how much is the variability of the random errors and how much is the standard errors of this estimators that you have obtained, and obviously you would like them to as small as possible, right? So you can see here there's this value here, which is here in the 1, which is here like as residual standard error as 18.65. This is obtained here like this one, right? And this standard error, these are the coefficients which you have taken the positive square root, and they are the values which are giving you here. So, right. So I think now I will stop here, and you can see here that I have given a very small, gentle introduction at this moment, and that was only a small section in the entire outcome. Well, it makes more sense when you have more than one independent variables. So in the next lecture, I will try to extend the same lecture for the original data set that we had considered, where we have 3 variables, and then I will be able to give you more idea that how are you going to choose the variables, how are you going to look at the values of for the goodness of fit, etc. So, but this was a pretty simple concept, but this concept is going to be used when we are trying to go in the setup of more than one variable, because here I can show you that what is my beta 0, what is my beta 1, and I can show you many things like as confidence interval, etc., test of hypothesis. But when we are going into the multivariate setup, then things have to be understood only from the brain. You cannot see from your eyes. So that is what I will try to show you in the next lecture. Now, if you have any question, you can ask me. And I'm extremely sorry for the hitch up in this one. So this laptop is the random error. That is the my example. X beta is my beta 0 plus beta 1. X is in my control. These are my slides. And then, yeah, so sorry for that.
So dear participants, if you have any doubts, please unmute and you may speak. Hello, dear participants. You may type in the chat window or you may speak to the sir directly. Sir, I have one doubt, sir. If you were mentioning about some variables, if to fit them properly, or if they are not influencing, we may remove or delete them and then again reconsider it. If we do such remodeling, sir, how will be how good are we making the model? Because initially we have started off with some modeling considering these parameters, and later on we are removing in and then redefining it. Yeah. So will that have any effect on the overall regression model that we develop?
Yes. Actually, because I will try to address in the next lecture. But the fact is this: when we start the regression modeling, I always say before you start conducting your experiment, you must consult a statistician and then try to explain the entire problem, that this is what you want to do. Based on that, as a statistician, we always try to find that which are the variables that are going to be important, in the sense they are going to contribute in your model. And then we try to fix certain number of variables. Now, definitely, if you increase the number of variables, the computational part also becomes inefficient. For example, conceptually, I can say that I can invert a matrix of 1000 by 1000, but in practice, it is very difficult. And there are certain algorithms, but there will be some, say, approximation error. But on the other hand, the rule is this. For example, if you know about R square, as you try to increase the number of variable, R square will always increase. So now the question here is this: you have to strike a balance that whether if you are trying to include even a garbage variable, this R square will increase and that will indicate that the model is getting better. But the fact is this: by adding the garbage variable in the model is not getting better. So this common sense, your experience with the experiment, and what is really happening in the experiment and statistical thing all go actually together. So whenever you are trying to do the modeling, you and your statistician both should sit together. You should have good interaction. As a statistician, I will give you the model and I will ask you, can this happen or not? Then you are the one who is going to tell me, yes, this can happen. And this thing happened in that experiment in the mechanical engineering. I asked, okay, I want the data with this voltage and with this current. Then my colleague simply said, okay, for this, we have to buy a machine worth of several crores. Then I said, okay, then you don't do it. But as a statistician, I don't know. I'm simply trying to gather all the relevant information. So when you try to do this, will always be you try to think of some model, go to whether it is as close as possible to your real things or not. Then you try to see, no, there is something wrong. The model can be linear, non-linear. You try to look into the variables. You try to delete.
Hello, sir. We lost you. The signal is weak, I suppose. Hello. Okay, I think signal is lost from sir's end. So if that is okay.